what we are now going to do is we're going to take this reaction time data, this button pressing time data, and we are just going to fit it to the model having specified the priors that I showed you earlier, right? So the code, of course, now is very easy, right? It's very straightforward. It's just like the linear model. I've got reaction time as a function of the intercept and the slope here, and I've defined my data frame here. The family is log normal. You have to be careful not to put a Gaussian here by mistake now, right? We are assuming a log normal, right? And you have to be careful to define the priors on the log scale. A very common mistake that I often see is that people forget that they're working now on the log normal scale and they start defining priors on the millisecond scale here. So if you put a 1,500 prior on the intercept, you're going to get really crazy output basically in the prior predictive distribution, because that's on the log scale, right? So be very careful about the prior specification and the scale in which you're working. Okay, so that's basically it. I mean, there's nothing more in this model that I need to explain. What we now need to do is to interpret the results of the modeling, right? So the first thing you should do is to plot the results to see what you get. With the plot function, you get a pretty nice summary of the intercept and the slope and the sigma parameter. The chains are converging nicely. You've got these fat, hairy caterpillars, right? So everything looks good here. And the diagnostics that they print out in the short summary, for example, the printed table, will also show you what the diagnostics are on the convergence, which is discussed in the lecture notes, so I won't discuss those here. So what's interesting about this figure, how do I interpret this figure, right? So what do I do? As a Bayesian, I'm basically interested in my uncertainty about this parameter, the slope parameter, right? So first thing to notice is that this slope parameter has very small values, so I don't really know how to interpret them. The reason that these are so small is that they're on the log scale, right? So it would be convenient if I could actually look at all this on the millisecond scale, because I cannot think about reaction times on the log scale and what the impact of 4 times 10 to the power of -4 is going to be, on the millisecond scale. So it's pretty easy actually to convert back to the millisecond scale. So imagine in the model, this is the fitted model that I have. This fit press trial is this model that I just fit, okay? So I can extract now the posterior distributions as vectors of data for each of the parameters. I've got the alpha parameter, the beta parameter, and the sigma parameter. These 3 parameters will have samples inside the model, which I can extract, and the function for extracting them from the model is this as draws df. It's very obscure, I agree with that. It's a very strange term to use. I would have preferred something like posterior samples, and in the past they used to have that in this functionality, but now they call it as draws df. So you're getting the intercept here. I'm saving that as a vector. I'm saving the posterior for the slope as a vector of values here. So these are vectors of values, right? And now the cool thing is that I can take the alpha samples. So this is the vector of the posterior distribution of the intercept parameter, and exponentiate it and subtract from that the effect of going from trial 0 to trial 0 minus 1. So the difference between one trial and the next trial in the middle of the experiment, right? That's what I can now get. So what is this? How is this working? What am I doing here? Well, what's happening is that, to quickly write this out, what's happening is that I am modeling log reading time, right, in terms of alpha and beta parameters with centered trial as my predictor, right? That's my model. There's of course an epsilon term there that I'm ignoring, right? So now I can compute, if I exponentiate both sides, what's the opposite of the log? It's the exponent, right? So if I exponentiate a log reading time, right, what will I get? If I exponentiate the log reading time, I get back everything on the log, on the millisecond scale, right? So if I do that to the right hand side as well, what I get is exponent here, alpha plus beta times centered trial, right? So this is the interesting part here, right? So remember, the alpha is telling me, the intercept parameter is telling me the average effect when we are at the middle of the experiment, when centered trial has value 0, right? So if I want to know what the effect is at the middle of the experiment, I just type this exponent alpha, right? Alpha is right now the posterior distribution that I have from the model, that vector of parameters that I have. And if I want to know what the difference between this reading time, this is a reading time in milliseconds, this is the milliseconds reading time predicted from the model, right? What is the difference between this reading time and the one trial before it? All I have to do is take this, subtract from it alpha minus beta, right? Because beta represents the change in the average reaction time or reading time or button pressing time with every unit increase in increase or decrease in the trial ID. In this case, decrease. So that's what I'm doing here, right? So that's what that code actually achieved, right? So if you look here, I'm doing this computation here, and so this is giving me the measurements on the millisecond scale. And then I can do some statistics. I can figure out the lower and upper bound, the 95% credible interval, the mean, and so on. So what I'm looking at here is the mean effect and the 95% credible interval in milliseconds. You can see that it's very small. What this means is that from going from the I-1th trial to the middle of the experiment, there is just a 0.08 millisecond slowdown, right, in button pressing time. So this subject seems to be getting slightly slower and slower, but very slightly from one trial to the next, right? So you can, of course, it's hard to understand what 0.08 milliseconds would be, right? It seems like a very small amount. So you could ask a question like, what would happen if I go from the middle of the experiment to 100 trials down the road? How much of a slowdown would I expect now? You can also compute that, right? So what I've done here is to show you another example. If you want to compute the difference between the first and the second trial, right? So you can extract the information for the first and second trial, and this gives you the estimate from between the first and the second trial, the change in the reaction time. But if I want to know what happens 100 trials downstream from the middle of the experiment, I can also do that now by just multiplying the beta samples with 100, right? And then subtracting that exponentiated term, the alpha plus beta times 100, from the exponent for alpha, right? The exponent of alpha, which gives me the average effect. So that's how I learn what would have happened 100 trials downstream, okay, going up to the middle of the experiment. So that's what the model predicts now, that when you move from trial n to n plus 100, you get a slowdown of about 9 milliseconds, ranging from 6 to 11. That's a pretty tight estimate, right? And so that's easier to understand on the millisecond scale. And so maybe this is important information now scientifically. If you're studying, for example, exhaustion effects, right? Are people slowing down as they're going through the task, right? This is the information that you're going to work with to draw inferences about the problem that you're studying, okay? Okay, so another thing, of course, you can do is to look at the posterior predictive distribution of the predicted median differences that I was just explaining, right, from n to n plus 100, right? So this is the observed effect in the data, right? That T of y is the statistic, that's the observed effect. And now we have, these are the range of variations that you see in the posterior predictive data. Remember that the model will produce thousands of predicted data sets internally, right? So we are looking at the distribution of this statistic in repeated generations of this data. This is a very useful thing to do, to generate future data sets from your model to understand what the range of variability is going to be in your model. You can also do this in the frequentist setting. It's not unique to the Bayesian approach, but it's an extremely important part of the Bayesian workflow, right? The prior predictive checks, prior specifications, sensitivity analysis, fitting the model, looking at the posterior distribution, and looking at the posterior predictive distribution. These are all part of the Bayesian workflow. There's a standard approach that we take to try to understand what our model is actually teaching us about the data, okay? All right, so that's it for this simple example of using a normal likelihood and log normal likelihood. Next, I'm going to move on to a very important topic, generalized linear models, but I will only discuss one example of generalized linear models. That is this very important case of logistic regression, which is kind of a bread and butter model for many of us in data science and in cognitive science, psychology, linguistics, many other areas.